This is the morning quiz review, 5.2 through 5.5. All right, so when we look at these problems here, integral antiderivative problems, first thing we want to try and do is look to see are there any available rules that will allow us to solve this uh, without going through use substitution. But if we look at this here, there's too many parts to this problem that prevents us from being able to just use one rule to apply. So probably want to try to use substitution to simplify the problem, and hopefully then it'll be easier to identify the appropriate rule to solve this problem. So if we want to go through use substitution, if we see parentheses, then the first guess should be the portion that's inside the parentheses. So in this case, if we let the u value be natural log of x, then the derivative of natural log is 1 over x, and that should help match and cancel out this x, which is causing this problem to have too many parts initially to solve. So let's let the u value be natural log of x. So then the derivative of our u value with respect to x, the derivative rule for natural log of x is u prime over u. So the derivative for x is 1, and then 1 over x. So with use substitution, after we identify our u value, after we find our du, the next step is to try and replace and convert everything to be in terms of u. So I'm going to go ahead and solve for dx and make that substitution. So if I solve for dx, I'm going to get dx, if I do cross product, dx equals x du. So now I'm going to replace natural log of x with u, replace dx with x du, and once I do that, I get integral of u squared over 5x times x du. Notice the x's cancel out conveniently, and then that leaves us with a problem that's a lot easier to solve. We now have 1/5 integral of u squared du. So from here, we only have one variable to deal with, and it looks like this is just a simple power rule for integration. So we go through power rule for u squared. So u squared becomes u cubed over 3, and then plus c. And then finally, we want to represent our answer in terms of the original variable given in the problem, so in terms of x. So we can replace u back in terms of x. So natural log of s quantity cubed over 15 plus c. Okay, number 2, we have the integral of 7x cubed plus 21x squared plus 7x all over x to the 4th, 4x cubed, 2x squared. Right, so looking at this problem, it looks like we're unable to simplify. There's too many terms in the denominator. We don't want to bring all this denominator terms up to the numerator and distribute. Just too messy to do. But what if we think about use substitution? So if we wanted to use substitution, what if we let the u value be the denominator? Hey, let's just see if this could work, because if we let the u value be the denominator, then we want its derivative to have some form that matches the numerator. So if we think about the derivative for x to the 4th, the derivative will be x cubed. It's always going to be 1 degree less. So let's try that. We'll let the u value be the denominator, x to the 4th plus 4x cubed plus 2x squared. We find the derivative of u with respect to x. So x to the 4th becomes 4x cubed, 4x becomes 12x squared, 4x squared becomes 4x. Now at this point, if we factor out a 4, we're then left with x cubed plus 3x squared plus x. And this begins to look a lot like our numerator. Not perfectly exact in terms of every term, but well, let's see if we can get these two terms to match. What if we take the numerator and factor out 7 out of each of the terms? So if we factor out 7 out, we get x cubed plus 3x squared plus x. And now we have these two parentheses matching up. So it's a perfect match. We can cancel all the x's out, and then now we're then left with a nice oh, by the way, after I factor out the 4, I solve for dx. So when I solve for dx, I get du over 4x cubed plus 3x squared plus x. So that's why this term is in the denominator. And then this entire expression replaces the dx. Since with use substitution, we're trying to piece by piece replace all of our terms in terms of u. So we have the parentheses matching up and canceling out, so that leaves us with 7/4 integral of 1 over u du. So we have a nice rule for this. For the setup, the integral of 1 over u is the one exception that that will not work with power rule, but we do have a natural log rule that matches. So that matches with this this setup. So the integral of 1 over u is simply natural log of the absolute value of u plus c. The 7/4 just tags along in front of the natural log function, and then finally replace our u value back in terms of x. All right, if we look at number 3 here, if we let the denominator try to be the u value, we see that the derivative is not going to match up with the numerator. If we let the numerator be the derivative, be the u value, the remaining parts is not going to match the denominator. So looks like this could be something that we could maybe go through either long division or synthetic division. So the nice thing about synthetic division is that it's a lot faster, and but however it only works if we're dividing by a linear term. So I'll walk through the steps for going through synthetic division. So what we can do is we can draw a half box, and then outside will be the factor, and the factor is going to be whatever causes this to be equal to 0. So in this case, x plus 2 is equal to 0, so x equals -2. And then we're going to bring down all the coefficients of all the terms. So this is 1, this is 3, -1, and then there's a missing term, so we have a placeholder for the x to the first power as 0 and -5. So this is a placeholder for the fourth power, third power, or third degree, second degree, first degree. So linear, there's no linear term, so we have a placeholder for that, and then finally the constant. Okay, so with so the next step with synthetic division is we can bring down the 1 below the half box, and then we can multiply. So -2 times 1 is -2. Combine those terms to be 1. 1 times -2 is -2. Combined to be -3. -3 times -2 is 6. 6 plus 0 is 6. -2 times 6 is -12. And then combined to be -17. The last term, that last value, is going to be the remainder. If we get a remainder of 0, then that tells us that this is a perfect fit. There's no x plus 2 factors perfectly into the numerator, but there is a remainder. So what we've done is now we've rewritten the problem, hopefully in the form that's a little bit easier to find integral rules for. All right, so because we're dividing everything by a linear term, each of these degrees are going to fall by 1 or go down by 1. So this is now, before it was x to the fourth, is now x cubed, so 1x cubed plus 1x cubed, yep, plus 1x squared minus 3x plus 6. And finally, the -17 is a remainder. So the way we write the remainder is -17 divided by the factor x plus 2, meaning that this cannot further divide anymore. So we've presented the problem now in a simpler form. All these are now separated by individual plus or minus signs. So these are individual terms that we can apply separate integral rules for. So power rule for each of the terms, and then this last term we can go through use substitution, and eventually will be a natural log problem. All right, so x cubed becomes x to the fourth over 4. We're going through integral power rules for each of these, antiderivative power rules. X cubed becomes x cubed over 3. -3x becomes -3x squared over 2. 6 becomes 6x. And then here, if we let the u value be x plus 2, our derivative is 1. Our dx equals du. And then we have the integral of 17 over u du. And then integral of 17 over u du becomes 17 natural log of u. And then replace our u back in terms of x. And then don't forget the plus c. All right, number 4, we have a definite integral problem. Here, though, if we try and distribute through, it looks like use substitution. If we let the u value be the entire denominator, it's not going to quite work. So we're going to try and test to see if maybe the use substitution for just the portion inside the parentheses will cause this to work. Again, a lot of times with use substitution, it's going to come down to trial and error and doing enough problems to kind of provide us with provide you with with maybe a better idea as to where the problem could lead. So we're going to try and test it out with the u-value being what's inside the parentheses. So we'll let the u-value be 1 plus x to the 1/2, the derivative. 1 becomes 0, so that goes away. X to the 1/2 becomes 1/2 x to the negative 1/2. If I clean this up, it becomes 1 over 2 root x. And then if I solve for dx, if I do cross product, I get dx equals 2 root x. All right, so now let's make our substitution. Remember, u substitution, we're trying to rewrite the problem in terms of u. So dx gets replaced with 2 root x du. Root x stays initially, and the 1 plus root x gets replaced with a u value. Now, we're at this point here. Notice the root x cancels out nicely, and we have a problem that we have a rule for, because now it's just integral of 1 over u, and we know natural log will take care of that. So integral of 1 over u is just natural log of absolute value of u, so the 2 just tags along, so 2 natural log of absolute value of u, and then we can plug in upper and lower bounds. So two options here. We can replace our u value back in terms of x, and then plug in the original bounds 9 and 4, or we can just try and find the answer in terms of u. If we want to just go evaluate the upper and lower bounds in terms of u, then we have to adjust our upper and lower bounds. So we have to go through a conversion. We have an equation that relates u and x together. So if I plug 9 in for the x, because these are originally x values, plug 9 in for x, so square root of 9 is 3, so 3 plus 1 is 4. Okay, and then if we plug 4 in for x, square root of 4 is 2, 2 plus 1 is 3. So we have our upper bound converting from 9 to a 4, lower bound converting from 4 to a 3. So now our antiderivatives in terms of u, our bounds are also in terms of u, so now we can evaluate. Upper bound first, 4 goes in for the u, and then so we get 2 natural log of 4 minus, then plug in 3 in for the u value, so 2 natural log of 3. And this is our answer. We can clean up a little bit by factoring out a 2, and then a little bit more because we can go through quotient property. So natural log of a minus natural log of b is same thing as natural log of a over b. All right, 5 is just recognizing integral rules that we can use here. So, but first, we have rules for cotangent of x, cotangent of u. We have a rule for secant of u. But let's go through u substitution first for each of these terms. These are terms separated by plus or minus, so these are individual problems that we can treat as separate parts. All right, we'll let the u value for the first portion expression be 3x, so u is 3x, so the derivative of u with respect to x is 3. Solve for dx, we get du over 3. So that's 2 integral of cotangent u times du over 3, and then the 1/3, the 3 can come out as 1/3, with the 2 becomes 2/3 integral of cotangent of u du. All right, secant of 4x, if we let the u value be 4x, then du over dx equals to 4. Solve for dx, dx equals du over 4. We can pull the 4 as 1/4, and then now we can apply the rule. So we have a rule for cotangent, which is natural log of sine of u. So 2/3 natural log sine of u minus the integral for secant of u is secant of u, natural log of secant of u plus tangent of u. So we have 1/4 from the coefficient, natural log, absolute value of secant of 4x plus tangent of 4x plus c. All right, number 6 is another u substitution problem. In this case, we're trying to match our rule. We're trying to, if we go through u substitution, our end goal is to try and make this look like an integral of a to the u. We have a base of 7 raised to an exponent. So if we let the u value be the exponent, then the hope is that the remaining derivative will help cancel out this x squared. All right, so let's try that. We'll let the u value be 2 over x. So if the u value is 2 over x, that's the same thing as 2x to the negative 1. The idea is we're trying to prepare this expression so that we can apply power rule for derivatives. So the derivative of u with respect to x becomes negative 2x to the negative 2, which is negative 2 over x squared. If we do cross product, we get dx equals x squared du over negative 2. We make our substitution. So integral of 7 to the u over x squared times, and then the dx gets replaced with x squared du over negative 2. Now notice conveniently the x squared cancels out. We have, unless the x's cancel out, we're unable to go through with the rest of the u substitution. So all the x's have to cancel out, otherwise we have to go back and rethink what another method is. But here in this case, our u substitution matches nicely, allowing us to eliminate that x squared. So now we have a nice clean problem that we have rules for. The rule for integral of a to the u is 1 over natural log of a times a to the u. So here we have negative 1/2 a to the u over natural log of a, in this case the a value is 7, plus c. And finally replace the u value back in terms of x. So negative 7 raised to the 2 over x all over 2 natural log of 7 plus c.